Welcome to this lecture on generalized predictive control law. We will minimize an index over a range. We will weight the control effort also. Let us consider the optimization index for GPC, generalized predictive control. Contribution to this index is from two sources. Contribution from error, it is given in blue. Control effort, that is given in black. We will begin with the error terms shortly. We will consider the control effort terms later. It is important to note that the error term is minimized over a range up to ny, whereas the control effort is minimized over nu. Usually nu is smaller than ny. In the subsequent slides, we might replace this ny with just n. This y hat is the estimate of the plant output or is the reference signal or the set point. So let us start with the error terms. Recall the prediction model that we arrived at in the last video. We will stack up the future set points and call them as r underscore. Subtract r underscore from both sides of the first equation and equate them to 0 because we want set point tracking. I have subtracted r from the left hand side. I have included one e also. We will see the reason for this e shortly. We will do the same thing on the right hand side and I want this equal to 0. The reason to introduce e is as follows. It is a non-square system, hence we cannot make this error absolutely equal to 0. We can only minimize E transpose E, that is, we will look for a least squares solution. So solve the following using the least squares approach. I have written this equation and I have written it in this form with this E. The least squares solution approach of course includes this E automatically. When I solve the rest of it by least squares, it is equivalent to minimizing this error. You may want to see the previous video in which we talked about minimizing this error and we presented a geometric solution. So let us continue with this equation. Least squares solution of this equation is given by this solution, where we have taken G transpose G inverse into GT times this whole thing. Recall the observation that we made while writing this form. We do not actually invert it, we only solve GTGU times this, that is the equation of the form AX equals B. Okay, this minimizes E transpose E, the projection error. This is only a partial solution because we have not considered the control effort yet. The complete solution is given in the next slide. So this is what we want to minimize. To reduce the control effort also, we need to minimize this modified objective function where we have included delta u terms also, that is changes in control effort as given earlier. We have to minimize with respect to E and also delta u. I have kept this as nu, whereas I have replaced ny with n as mentioned earlier. To minimize this with respect to delta u also, let us differentiate with respect to delta u, equate to 0. We get an equation of this type containing only delta u terms. both conditions on U have to be satisfied, namely this condition which minimizes E transpose E and the second one that minimizes delta U. We have to stack these one below another and solve. We have delta U here, but we have underscore U here. So how do we combine these two? Recall the definition of U underscore. It already has delta U terms. We can see it in the next slide. This is the definition of U underscore. This is the stacked set of two equations. We need to solve this in least square sense. So because U underscore contains delta U terms, the second equation in this matrix equation minimizes delta U terms. So let us solve this. The least squares minimization solution to this system is given by the same formula, transpose of this matrix into this matrix, inverse multiplied by transpose of this matrix and this entire right hand side. When I simplify it, I get this, because you can just multiply this out, you get this inverse, you multiply this and this, the second term gets cancelled, so you get GT times this whole thing. So this is the solution that we are looking for. Okay, this is what we arrived at in the last slide. Control effort U is given by this, whereas this control effort is in the form of delta U terms. Now that can be written as some K times this whole thing, and what is this K? This K is the first half of this expression, which is this inverse times GT. So this is the control law. We calculate the control law, after that implement only the first row, that is only the delta U terms. When I solve this, when I calculate this, I will get a vector. I will have expressions for all these delta U terms, but we will implement only the first row, that is only delta U n at every time instant. This is known as the receding horizon control. As we go to the next step, the interval over which we will minimize will also shift. So it is known as the receding horizon control, and we implement only the first row here, that is delta U n. Here is the schematic of the method that we have proposed. What is given in red is the reference trajectory. We don't give a direct set point change. Here is the measured output. This is the current instant, because whatever happened here until now is already known to us. If our control law is good, our prediction will coincide with the required set point trajectory. Here is the predicted control effort. We will implement only the first control effort, first control move. So I have taken this from Wikipedia. To conclude, GPC belongs to a class of controllers known as Model Predictive Control, or MPC. GPC uses sophisticated noise models. We will also see DMC, that is dynamic matrix control, that uses an approximate noise model. MPC is popular in chemical and oil industries that have sluggish response, model uncertainty, delays, and slow drift in model parameters. With this, we have come to the end of this presentation. In the next presentation, we will solve an example. Thanks for joining. Goodbye.